People have developed clever ways to improve the angular resolution of a stepper motor. The simplest pattern, shown in the graph to the right, moves the rotor one full step at a time. Hence it is called a full step operation. The phase currents are alternating between plus and minus polarities, so that the drive method is bipolar as opposed to unipolar. A full step operation provides the highest torque because all the stator coils are energized at the same time. This attracts a rotor tooth midway between two stator poles. Note that the graph is showing the RMS current, plus 70.7% and minus 70.7%. When the phase polarities are changed, a rotor tooth is attracted to the next closest midpoint between the two stator poles. When phase 2 current transitions from negative to positive for the first time, the square wave representing the step input has already gone through one full period. The step angle for a stepper motor is cut in half when you use a half-step drive. You get twice as many steps per full revolution of the rotor than with a full step drive, and thus twice the resolution. The graph shows a half-step drive with two phases. One phase is energized, then both are energized, and then back to just one energized. In this way, a rotor tooth is attracted first to the closest midpoint between two stator poles, then to the closest pole, then to the next closest midpoint between two stator poles, and so on. Be aware that the holding torque of the half-step method is much weaker than with the full step method. The rotor teeth are farther away from the stator phases, and so the magnetic attractive forces are weaker. A strong external load can throw the motor off its half-step position. In microstepping, we create a quasi-sine wave out of the current in the stator poles. We also place the current to the stator poles out of phase. In this example, there are two sets of stator poles, and the current to them is 90 degrees out of phase. This has the effect of slowly modulating the current in each stator phase. You get smoother motion and much finer step angle resolution than with either full or half-step operation. The rotor locations are interpolated between those of half-stepping. On the downside, you need specialized motor driver firmware to accomplish microstepping. In addition, the torque output will be lower than a full step or half-step drive. The design trade-off in stepper motor drives is between high torque output and fine pitch angular resolution. You can't get both at the same time. You get the highest torque output with the full step drive, but the worst resolution. You get the lowest torque output with the microstep drive, but the best resolution. The half-step drive leaves you in between. As always, the choice you pick depends on the needs of your application. You can buy a stepper motor driver chip that converts logic level signals to current sufficient to drive the motor. The digital input can be as simple as a command to go forward, reverse, or rotate a step, or more complex like an I2C or SPI interface. This slide shows an example of a driver chip. The transistors shown previously that form the H-bridge of a bipolar motor drive are all located inside the chip. As such, it works solely for small, low-voltage stepper motors found in cameras and other portable battery electronics. The input voltage range is from 0.3 to 10 volts, and supply current goes no higher than 35 milliamps. The saturation current is only 400 milliamps at a saturation voltage of 0.4 volts. This gives a maximum power of only 160 milliwatts, small enough to keep this small chip from overheating. The chip has some interesting features. It has an internal electric brake function for the motor, which can stop it much faster than if you shut off current and let the motor coast to a stop. The brake uses transistors to briefly short the motor terminals. The back EMF of the spinning rotor creates a reverse torque that brings the motor to a very quick stop. The spark killer diode is a reverse-based diode whose purpose is to dampen out a coil current caused by an abrupt open circuit. Historically, a spark killer was a capacitor and resistor connected in series across two high voltage points where electrical arcing might occur in a circuit. It was meant as a safety device for preventing ignition of components. In this case, the phase spark killer is extended to a diode whose basic function is still to limit current. We discussed thermal shutdown circuits in our video on AC motor control components. Coil windings in a DC motor can sustain damage from overheating, just like those in an AC motor. So the thermal shutdown circuit in this chip is very useful. Here's the block diagram for our driver chip. The chip can drive two coils at once, so it has two H-bridge transistor networks on the right side of the diagram. The coils are depicted with two letter M's inside circles, one between pins out 1 and out 2, and the other between pins out 3 and out 4. You have two pair of digital inputs to communicate a desired coil voltage to your motor coils. The controller converts those digital inputs into analog voltage levels for the coils. You can try to develop your own stepper motor drive electronics using driver chips and your own custom firmware, but the effort can be large. If you're not up to the challenge or you simply don't have the time, turnkey drive electronics can be purchased along with a stepper motor. It will come with options for full step, half step, and various versions of microstepping. You need to spend some cash, but you save a lot of time and effort. Choose your option accordingly. This slide shows an example of a commercially available stepper motor drive. It comes in a convenient enclosure with wiring terminals for the leads to the motor. Torque is highest when the motor is stationary and decreases non-linearly as stepping speed increases. Power is the product of speed and torque, and it peaks in the middle of the speed range. Motors can be programmed to rotate clockwise or counterclockwise in full steps, half steps, quarter steps, eighth steps, or 16th steps. Stepper motor drives typically use a full H-bridge circuit. This means that it applies a single voltage, power and ground, to each of the four motor leads. Let's recap. Now you've taken a deep dive into stepper motors. In the next video, we will have another lab exercise in store for you, this time using a mechanical rotary sensor.